So we briefly discussed about different aspects of processors in last class. We discussed about CISC and RISC architecture also. Then now we'll start with the multi-core processors. Okay. So why multi-core processors? Why should we go for it? That is a basic question. Okay. Nowadays, any device you take, there are multi-core. So the CPU architecture is evolving, the frequencies are increasing, pipelines are increasing. So when clock frequency increases, power consumption increases. That's a very important thing. Okay, basically when voltage and clock frequency increase, the power consumption increase. Now, first of all, chip area will also increase, power consumption will increase, cooling will be a difficult affair. Okay, so then why should not we have multiple cores operating in parallel at lesser frequency? So these are some of the motivations for going for multi-core processors. So the architecture generally looks like this. So there are multiple cores. Each core is a CPU by itself. Okay, and they'll have their instruction and data cache. So core 1, core 2, core 3, like that it will be. And they'll have a common instruction and data cache also. So each core will have their own instruction and data cache, and there is a common instruction and data cache. That is the way basically these cores have their own architecture. So from hardware perspective, the multi-core processor system, it can be homogeneous or heterogeneous. In homogeneous, all CPU cores are of same architecture. In case of heterogeneous, the CPU cores are of different architecture. From software process perspective, you can divide them as asymmetric multiprocessing and symmetric multiprocessing, that is AMP and SMP. Okay. So an AMP system looks like this. This is an AMP multiprocessor core. There are core 1 to core n. So the cores can be of homogeneous or heterogeneous type. Okay, and each core has their own address space, and they can be of different architectures, right? So here, since each core is of different architecture, you can have different type of operating system running in each core. For example, one core can be of DSP and other one can be of a different architecture. And because of this, in one core you can have, for example, Linux, then Android, then its own applications, where some other operating system like Nucleus, then its own middleware and its own application you can have in another set of architecture. So you cores. Okay, so that is what AMP system is all about. In case of SMP, the cores are of homogeneous in nature. It is basically getting into splitting the high frequency or high performance CPU into multiple lesser performance cores of same architecture. Okay, so these CPU cores share the same memory space, so we can very well have one operating system running on the multi-core. That is called, that's why there is a version of Linux called SMP Linux, which is available to run on this kind of system, that is SMP system. Okay, so in SMP system you cannot have multiple operating system running simultaneously. This is an example of ARM MP core, ARM 11 MP core. So this has been taken from ARM website. So you can see these are say this CPU, and it has its own L1 memory. Each CPU have their own L1 memory, and there is Snoop control unit. So this snooping unit looks at writes from processors, and it will try to make a synchronization between all the processors, because there are possibility that this processor will be writing to the memory simultaneously, right? So there should be some unit who should synchronize the writes and update their own instruction in data caches, right? So that Snoop control unit exists to reflect the latest status of the memory for every processor. Okay. Similarly, it has an interrupt dispatcher, and this interrupt dispatcher's job is to route the right interrupt to the right processor. So probably you can go to this website and try to see more about this particular architecture, which is from ARM. And now we talked about multi-core processors, and then there are different type of specific processors. One of them is DSP processor, and DSP processor generally they are used for vector operations, that is more multiply and accumulate kind of thing. If you see, this is a type of DSP instruction where you are calculating a vector product. So you see there are a lot of multiplication and additions are involved. So multiply and accumulate is a feature of DSP processor. And DSP processor generally go for Harvard architecture. The speed is very important in case of DSP processor. And they'll have SIMD, that is single instruction multiple data kind of architecture. And they are primarily of VLIW architecture, that is very large instruction mode architecture. They will have pipelining, they will have saturation arithmetic, and they will have specific instructions or specific execution units which will make sure that minimum overhead looping is there, low interrupt latency is there, context switching is faster, and register banking. Register banking is basically without copying from register one register to other, you can change the type of register on the fly. Basically, some register may be input and you program the processor in such a way that they become output for some other function. Okay. So, sorry, I told differently. Some others are output of one function, and if you program the processor in such a way that they'll become input to another function. So this will remove the operations where the data to be copied from one register to other. Okay, and of course it will have cache and DMA. So this is an example of SIMD instructions. So in SIMD, generally, if you take the example of multimedia instruction, what happens in that case? In those scenarios, you have to do addition of multiple data simultaneously. For example, if there is a 8x8 block of data, so, and you have to perform some operation on that, what you have to do is you have to basically take each of these bytes and perform the operation one by one. But if there is an instruction which is available which does the same operations on multiple data simultaneously, then things will be faster, right? So that is what SIMD does. So for example, in this case, you can see this is a column vector A0, A1, A2, A3, B0, B1, B2, B3 is another column vector. You want to calculate A0 plus B0, A1 plus B1, A2 plus B2, and A3 plus B3. In a normal processor, you have to have a loop which will be running 4 times and you will be doing that add operation, right? But in case of SIMD, what happens? This operation happens in one instruction because there are instruction pool is one, but the processing unit, there are multiple processing units which are doing the same operations. So multiple data are coming and they are getting what you can say that the operation is happening parallelly in these processing units. So you are getting a faster performance in case of SIMD. Okay. Then in VLIW architecture, these are the most common architecture for DSP processors. So VLIW stands for very long instruction mode. It exploits instruction level parallelism. Okay, so that means multiple instructions can be executed at the same time. So it has multiple execution units in parallel because it is trying to take instruction level parallelism advantage. Okay. Hence, you should have multiple register files also, right? So there is one instruction one. You remember I was talking about the instruction decoding. So when instruction is fetched, it comes as an instruction word. Okay, so that instruction word has to be decoded by the instruction decoder. So in case of VLIW, what happens? A pack of instruction comes as one long instruction. Okay, and these instructions are separated out at the execution unit. We can probably go to a diagram. So you can see here is from instruction program memory it is coming, and the long instruction one is fetched, which is of 8 instruction, and each instruction is of 32-bit wide. So they are fetched, and each instructions are separated in this unit, this fetch, decode, and dispatch unit, and issued to different execution units. That is the way VLIW architecture works. So the instruction word is one, and they finally get separated into multiple instructions, and the instruction operations happen in parallel. Now we have seen that there are cases where there are dependency on instructions, right? Multiple instructions, so one instruction is dependent on other one is dependent on other. So it is not necessary that all the instructions can be executed in parallel. So there should be some way out to find out which are the instructions which can be executed in parallel and which cannot be not. So this is the job of the VLIW compiler. So VLIW compiler, what it does is it reorders the instruction and create parallel pools of instructions, which will of course not hamper the instruction flow. So that means the instruction which can be executed in parallel without harming the dependencies, compiler takes them and it reorders the instruction accordingly and issues to the VLIW processor. Okay. So in this example, you can see this is an example. In fact, this is the instruction pipeline for TMS, that is TI's DSP processor, one of the TI's DSP processor, and it has multiple units. You can see L1, S1, M1, and D1, and L2, S2, M2, and D2. So the two parallel units, execution units it has, and in fact, things can be executed in parallel between L1 and S1 and L2 and S2, etc. So such parallelism are there, and each instruction there will be like restriction, like okay, these instructions can be executed in L1, this cannot be executed in D1, like that. So such restriction should be understood by the compiler, and compiler will make them parallel. So because there are parallel execution units, there are so many registers also. So they are called register files. Okay. So these register files are used for execution of these instructions, and finally data comes to the internal data RAM. So this is one more way of viewing VLIW architecture. So the instruction is coming. This is the instruction word. Then from instruction words, each instruction is issued to different execution units, and this execution unit use the register files, and finally output comes out. Okay. There is one more type of fast CPU architecture, that is called superscalar architecture. It is similar to VLIW architecture. Here also there are parallel execution units. The only difference is that the instruction words are also different. So that means separate instruction words comes and they get decoded and dispatched to this execution unit. Whereas in case of VLIW, if you see, there is only one instruction word, and that instruction word is getting decoded properly. Here, each instruction separately they come and they are executed through separate execution units. So in case of superscalar architecture, what happens? The reordering of the instruction is the responsibility of the hardware, that is the dispatch unit, which can be made parallel. Whereas in case of VLIW, reordering of the instruction to exploit the parallelism is the job of the compiler. Okay. So this is what is the difference between VLIW and superscalar architecture. so which I have already explained. So VLIW has a single and very long instruction word, whereas in case of superscalar there are multiple instructions. And here in VLIW, compiler does instruction reordering, whereas in superscalar hardware does the instruction reordering. So in this VLIW case, it is static instruction scheduling, whereas in case of superscalar, it is dynamic instruction scheduling, because hardware will do it dynamically. Okay. So we talked briefly about processor technology. So let us go to the next important part of hardware of a real-time system, that is memory. So you definitely will be knowing that memory accesses have the major contribution in latency. Basically, if you want to make a system faster, then look at the memory accesses rather than looking at how fast the processor can perform. Of course, you have to look at how fast the processor can perform, but memory, having a very fast processor and very slow memory access will not improve your system, rather it will be limited by the memory access. So it becomes important when utilization factor is in the dangerous zone, right? 83% to 99%. It is, if you remember the first lecture, I think first or second lecture. Second lecture, I have shown a table where the utilization factors have been given. Okay, anything beyond 69%, we slowly get into danger zone. Of course, when we tend towards 100% of utilization, we are getting into extremely dangerous zone. So if the utilization factor is getting into this zone, obviously, can we do something? What are the options? You increase the speed of the CPU. It is not possible, and CPU is costly. So what you can do? Can we have a better memory organization so that the total execution time is reduced, and hence we will have a better utilization, means the utilization factor will reduce. Okay. So because of this kind of reason, we will have hierarchical memory architecture. I'll discuss about it. What is hierarchical memory architecture? And we must understand the memory technology so that we will choose the right type of memory for the system. Okay. So there are different types of memory. I think you would have been reading from your college days, and since you are working, you will be encountering this very often. So just I'll give a summary. It is more of a recalling those concepts. Okay. So the traditional distinction is like this: ROM and RAM. ROM is read-only memory, which is non-volatile. RAM is random access memory, which is volatile. Okay. Now ROMs use generally the earlier days. ROMs get used to program once at the beginning using special programming unit, some kind of a UV unit, which will be basically, you can say, putting the data permanently in the ROM. But now, no more those techniques are required because we have EEPROMs and flash memory. So these are also non-volatile memory, and we can electrically erase them and write them, right? So at present, if you see, different type of memory which are used are non-volatile. Primarily, they are EEPROMs and flash, and volatile, which are basically RAMs, and RAMs are of two types: DRAM and SRAM. Okay. So SRAM is static RAM, DRAM is dynamic RAM. So non-volatile memories are actually here. One thing is that yes, electrically they can be rewritable, they can be erasable and writable again, but they are so slower than RAMs. RAMs are very fast. So, and there is a limit for each of these non-volatile memory. Generally, this how many it is? 1 million to 10 million times you can do read and write on. Sorry, rewrite, not read and write. So you can erase and write this many amount of time. So there is a limit to it. So that is the reason why EEPROMs are usually used for storing non-volatile programs and parameters. Generally, some parameters we want to persist across on and off, then we use EEPROMs for them. And flash memories are usually used for storing application programming data. Okay, so generally the operating system and its associated application will be there in flash, and during booting, the booting system, the bootloader, that is, it will load this operating system from the flash, and generally in flash it will be in a compressed form. So it will this bootloader will uncompress it and load it to the RAM. That is the way it is done in embedded systems. Okay. So by the way, this context here is embedded system, that is real-time system. That's why I'm not talking about disk memory, because disk memories are usually present in the general purpose system. So this is what I talked about. So it is a common practice in many real-time systems to load the application program, including the operating system, from flash memory to the RAM and then run it from the RAM. Okay. And in many cases, these flash memory are also movable one, that is SD card or USB memory sticks. Sometimes we boot from USB memory also, right? Sometimes a software upgrade is done through USB sticks. So this is a brief discussion about the non-volatile memory. Now come to the volatile memory. Volatile memories are primarily SRAMs and DRAM. So SRAM is static RAM, and it is made up of typically 6 transistors. Okay. Whereas DRAM cell has single transistor and capacitor. That's why DRAM is cheaper. SRAM is costlier. Okay. But SRAM is fast. DRAM is slow compared to SRAM. And on the other hand, SRAM takes more chip area and DRAM takes lesser chip area, right? So this another factor is that DRAM has issue of leakage because of their capacitor. So this DRAM has to be refreshed periodically. So what happens? This is a basic thumb rule. While designing the RAM subsystem, the basic rule is that if you need a large amount of memory, then use DRAM. Otherwise, go for smaller system, you can go for SRAM, because the cost will not be much, because it is a smaller system and you will have a faster response. But what is generally it is, if you see from CPU perspective, it is done is the cache memories are primarily SRAM, whereas the RAM memory is primarily DRAM, means basically where you download the operating system and run it. So those are generally DRAM. Whereas all the cache, they are SRAMs, because you need a faster access between CPU and the cache. So DRAM as such, it evolved. It was like as time goes on, we get a improved version of DRAM. So like initially it was a FEM DRAM, then EDO DRAM, then SDRAM, then DRDRAM, and now the era of DDR. So DDR2, DDR3, like that, we are getting DRAMs nowadays. What is memory hierarchy? I was talking about memory hierarchy improves the access time, right? So if you see, CPU clock rates are increasing at a faster rate compared to the DRAM access time, right? That means CPU frequency are increasing at a faster rate compared to DRAM access time. So programmers always obviously desire the faster and infinite memory. Now what to do? The solution is memory hierarchy. So what you do, from fastest to slowest memory, you organize the memory. So the fastest one should be the internal CPU memory, register, then cache memory, then go to main memory, then memory on the board of external devices. Okay. So this is a kind of hierarchy, you can say, so fastest to slowest. So how it is done generally? So you can see the concept of cache come into picture, because that is what memory hierarchy, the memory hierarchy revolves around basically the concept of cache. So cache is basically a memory which is very near to the CPU. So it relies on the principle called locality of reference, means if there is a faster memory and data is available there, then CPU will take lesser time to access it, right? So locality of reference, it is referred to the address distance between the memory. So address distance between the memory between consecutive code and data access, means if CPU has access some memory now, and if CPU need to access the data which is near to that particular memory, then CPU can fetch all these data at a time, right? Generally data are not fetched in byte by byte. They are fetched in blocks generally. Okay. So if the data and code which are actually accessed frequently and they are nearby, if they reside in the same place, obviously the locality of reference will be low, then the access to it will be faster. That is what is the principle of cache. Okay. So it cache is a relatively small storage or of fast memory where frequently used instruction and data are kept. Okay, that is what cache is all about. So how this operation of cache happens? So suppose CPU requests the content of a DRAM, and first the cache controller, you can see the cache controller checks the address to see if the particular location is already fetched in the cache. If cache controller finds that particular address, then in the cache, then what it does is directly it reads from the cache and give it to CPU, or if when it is a CPU write is happening, it writes to the cache and later it updates in the corresponding memory area. If this address is not in the cache, then what happens? A cache miss occurs, and because of that event, what happens? It fetches from the main memory and loads that in this particular cache memory. And at that time, probably because cache memory is limited, so it applies a principle through by which it erases the probably the least frequently used data from that particular cache in order to load the new data. Okay, that is the way basic operation of cache happens. So between cache also there are hierarchy. It is not just a one cache. There is something L1, that's something called L1 cache, which is the nearest to the CPU, and then next one is the L2 cache, which is little far away from the CPU, but it is nearer to the CPU compared to the main memory. So what you can say in the memory hierarchy, first one is the CPU registers, then and CPU's internal memory, of course, then the L1 cache, then L2 cache, then the main memory. That is what is the memory hierarchy. So with this, because the frequently accessible data is there in the cache memory, and cache memory have faster memory access time, the overall memory access time improves. So let us little bit understand about the cache access time. So let us define these terms. Let T main be the access time for the main memory. Then TL1 is the access time for the primary cache, that is L1 cache. H1 is the heat ratio of the primary cache. Means heat ratio means the percentage of time you can find the data in the L1 cache. Okay. So similarly, TL2 is the access time of the secondary cache. Sorry, it should be, there is a typo, it is secondary cache. And H2 is the heat ratio of the secondary cache, but not the primary. Means if it is not available in the primary, what is the heat ratio? Okay, that is, it's a conditional heat ratio, you can see. So if the system has only L1 cache, the average access time is nothing but H1 into TL1 plus 1 minus H1 into T main, because 1 minus H1 is the ratio of miss, right? So L1 cache miss is the 1 minus H1. So that is the percentage of time it has to access the main memory. So average access time will be H1 into TL1 plus 1 minus H1 into T main. Okay. If it has L1 and L2 cache, the average access time is similar, H1 into TL1, then H2 into TL2, and 1 minus H1 minus L2, because H1 minus H2, this is the miss percentage, okay? So miss ratio, that is. So this into the T main, that is the formula for L1 and L2 cache. Let us take an example. So here, there are, in this example, there are two levels of cache. The L1 cache has a heat ratio of 90%, and L2 cache has a heat ratio of 97%. Okay. The L1 cache has access time of 4 nanoseconds, the L2 cache has access time of 15 nanoseconds, and the main memory access time is 80 nanoseconds. So what is the average memory access time? Okay. So H1 is 0.9, you can see 90% is 0.9. Now what is H2? If you see, H2 is heat ratio of secondary cache but not primary. So it is nothing but H2 means this is the miss ratio of the first L1 cache. So and it is the heat ratio of L2 cache. So if L1 cache is missed, then only we will go for L2 cache, right? So the overall heat ratio of L2 cache means the effective heat ratio of L2 cache is nothing but the heat ratio of L2 cache when there is a miss in L1. So that's why it is 1 minus 0.9 into 0.97, which comes to 0.097. So 0.097 is H2. Now TL1 is straightforward 4 nanosecond, TL2 is 15 nanosecond, Tmin is 80 nanosecond. So apply the formula. So it comes out to be 5.295 nanosecond. Okay. So this is the average response time or average memory access time when there are L1, L2 cache with these heat ratios and their access times. Okay. So any doubt till now? So then we discussed about memory briefly. The next one is peripherals. So let us get into peripherals. So the first peripheral comes out to be interrupts. So what is an interrupt? So hardware interrupt is an external hardware signal that initiates an event. I believe you all know about interrupts. Each interrupt is associated with an interrupt vector address, okay, which contains the interrupt handler's routine. So whenever an interrupt occurs, that particular the CPU jumps to that particular address and executes the code which is present in that particular address, which is known as interrupt handler routine. Interrupt handler routine is a program for the desired action to be taken when interrupt occurs. There are software interrupts as well which are generated internally. Okay, so a typical interrupt service process is like this. First, interrupt request line is activated, then interrupt request is latched by the CPU hardware. Then processing of ongoing instruction, which is if there is something is going on, it will be completed. Then content of the program counter register is pushed to the stack, because that means it is a context switch happens. Okay. Then content of the status register also pushed into the stack. This is part of the context switch. Then the PCR is loaded with the interrupt handler address. Okay. Then when PCR is loaded with interrupt handler's address, automatically in the next clock CPU will start executing the interrupt handler. Okay. Then original once it is done, original content of the status register and PCR pop back from the stack to continue the operation which is going on. Okay, this is a typical interrupt service process. So we can look at this from a like block diagram perspective. So you can see that we talked about one interrupt, right? So CPU will have some few interrupt lines, but we may have multiple peripheral devices which we would like to interrupt the CPU. Generally, these peripheral devices operate in interrupt-driven mode. Whenever they have something, they'll interrupt CPU. Then CPU will execute the requested action by them. Then they'll go back. Do something like that. Take an example of the Ethernet controller, right? So whenever packet arrives, it will interrupt the CPU. Then CPU will process the packet. That is the way it will happen. But if packet doesn't arrive, then it need not interrupt it, right? So why to waste time? So they always operate in interrupt mode. Now in that case, what happens? We have many peripheral devices, but CPU will have few interrupt lines, but we require more interrupt lines. So that's why another peripheral chip comes into picture, which is called programmable interrupt controller. So this we can have more number of interrupt lines, and it will multiplex the interrupts and send to the CPU on one line. Okay, and obviously this will have its own registers, so to identify which interrupt has occurred. So it will correspondingly, in memory there will be interrupt vector addresses in the form of an interrupt vector table for each of these interrupts. So when it comes, CPUs jumps to those vectors as per the interrupt which has occurred. And among these lines, we can have interrupt priorities. For a more critical task, we can, or more critical interrupt, we can give higher priority, and for less critical interrupts, we can give lower priorities. Okay. So this example of Such a programmable interrupt controller, or PIC in short form, is 8059, which is used for x86 architecture. Okay. Another important peripheral operation is direct memory access. Generally, direct memory access is used in cases where there is a block transfer of memory. For example, access to computer memory is given to other device in the system without CPU intervention through DMA. Okay, because all these peripheral devices, again, they also require some memory operations. For example, for an Ethernet controller, when a packet arrives, it interrupts the CPU, but the packet data has to also be copied to the CPU memory. Now, how to copy that? One way is to do a byte by byte copy, right? But that will slow the process. So there is a mechanism which is called direct memory access, where CPU does not intervene, but there is another peripheral chip which is called DMA controller. It will take the control of the address and data bus and does the memory transfer without involving the CPU. That is what DMA is all about. Okay. So since CPU participation is not required, data transfer is fast. Okay. And DMA is the most preferred data transfer method in most of the peripheral devices. So see, this is an example of the DMA transaction. So it's a timing diagram, you can see. Okay. The time is the direction of time is this, or you can say it is a sequence diagram in UML's terminology. Okay. So there is a IO device, which is a peripheral device. It wants to do memory transfer, direct memory transfer. So what it does, it sends a request, DMA request, to the DMA controller. DMA controller is another chip, by the way. Okay. So then it sends a DRQ signal, and then DMA controller receives it, and it requests for the bus to the CPU, that is BREQ signal. Okay. So once CPU receives this signal, what it does is, if CPU has its any bus cycle CPU is doing, it finishes that bus cycle and sends an acknowledgement, which is called BACK, to the DMA controller. After receiving the B acknowledgement signal, what DMA controller does is, it sends a D acknowledgement, that is DMA controller acknowledgement signal to the IO device. Now this is a confirmation from CPU side is that yes, bus is free for you. Use the bus do the data transfer to the memory. So then IO device starts transferring the data from or to whatever its own memory to the CPU memory. That is the way basically DMA transactions occurs. Okay.